Hi, our last day in this chapter on polynomial functions and their graphs, today rational functions and their graphs, is to do some modeling with them. As we've said, I believe modeling is why we do mathematics. It's why we learn it, so that we can solve problems. And today we're going to be looking at some functions that can be modeled, or some situations that can be modeled with rational functions. So, a company is planning to manufacture wheelchairs that are light, fast, and beautiful, which would be a good thing. The fixed monthly cost will be $500,000, and it will cost $400 to produce each radically innovative chair. Write the cost function of producing X wheelchairs. So if you think about this, it's asking us to write an expression for the total cost involved. And the total, well, that has to be equal to their fixed costs. Things like building upkeep and salaries and things like that. Fixed costs plus manufacturing costs, and that's the $400 per chair. So let's see if we can write ourselves an expression that says that. C of x, or the cost, will equal. Their fixed costs are $500,000. And for each chair, and they're making x of them, for each of x chairs it's going to cost $400. Okay? For each chair, $400. The average cost per unit for a company to produce X units is the sum of its fixed and variable costs, that's this, divided by the number of units produced. And now it says write us an average cost function, and they use the bar to represent average. So our average cost function would take our total costs, which we just figured a moment ago, and we want the average price per chair. So what we should do is divide all that by the number of chairs we produce, and you can see that that is going to give us an average cost per chair. So now we have some instruction. We're supposed to find and interpret average cost for 1,000 chairs, for 10,000 chairs, and for 100,000 chairs. And before you start running off to do that, I'd love to have you think about what should happen. The more chairs you produce, what should happen to the average cost of each. But I'm going to go to my calculator, not my TI calculator this time, but instead my Windows calculator. And let's see, I want to have X of 1,000. So the way this calculator works, I need to do 400 times 1,000. That has to be added to the $500,000 in fixed costs, and then we want to divide that by the number of chairs we're making, which is 1,000. And we have $900 per chair on the average if we produce 1,000 of them. Folks, that's pretty pricey. I'm not sure that a lot of people are going to buy our chair at that price, so it really will probably be in our best interest to make a few more. This says let's try 10,000, so it's $400 per chair this time, times 10,000, and we want that added to the fixed costs of 500,000. And this time our division is going to be by the 10,000 chairs that we are making. So when we increase the production amount to 10,000, we have halved the price of one car. $450 was that average. And as we make 100,000 chairs, I would imagine that we're going to see that price go down even further. You might be thinking, as I'm putting this in my calculator, I wonder if there's a lower limit. How low could it go? $100,000 or chairs, sorry, added to the 500,000 in fixed costs, and divided this time by 100,000 chairs. 405. Oh boy. We got a drop, but it's certainly not as large a drop as we saw before. What do you think, folks? Here's our cost function, average cost per chair function, what would the horizontal asymptote for this be? To find it, because that's what this is asking, to find it, we'd have to divide everywhere by x, because that's the highest power of x in the denominator, and I am going to do that out here on the side. 500,000, even though that's a very large number, as x gets extremely large, it doesn't matter how big we are on top. X can always exceed that by a lot. That's going to go to 0. 400x divided by x is 400. So we have 400 on top in our asymptote. And on the bottom, x divided by x equals 1. So our horizontal asymptote would be $400. Can you describe what that represents for the company? I'll bet you can. Since this is the lowest cost to produce a wheelchair. Cost per chair will never go below $400. Cost per chair can't go below $400. All right. So we have a word problem, a rational expression, a rational function fits it very well, and we can tell a little bit about that production scene just by looking at that rational. Here's another example of the same kind of thing. If an object moves at an average velocity, the distance s covered in time t is given by the formula s equals vt, or distance equals velocity times time, which should be familiar to us. If you solve this formula for t, you would divide by v on both sides, and that tells you that time would equal distance divided by velocity. Correct? Distance divided by velocity. So let's look at this situation. Suppose a commuter drives to work a distance of 20 miles and then returns again on the same route. So we're traveling 20 miles. Our distance is 20 both times. The average velocity on the return trip was 10 miles per hour slower than the average velocity on the outgoing trip. Express the total time required to complete the round trip as a function of the average velocity on the outgoing trip. So if you think about that, the total time, TT, that's got to be the time that you spent going and the time that you spent coming home or returning. And we know a little bit about those things. Specifically, we know that the time going would be distance divided by velocity, and the velocity is what we don't know here, so x. The time to return, well, that's that 20 miles still, but this time we're going 10 miles per hour slower, so the velocity is x minus 10. And I believe that we've done exactly what it says. Express the total time required to complete the round trip as a function of the average velocity on the outgoing. Okay, we had a function that said the total time, total drive time, will equal 20 over x, where x is your speed going, plus 20 over x minus 10, where that's your speed coming home. Suppose we wanted our drive time to be no more than 60 minutes. We're not going to drive any more than an hour to and from work. Okay? At what speed should we drive? That question could be answered here. We want our total time to be 60 minutes or 1 hour. We want that to equal 20 over x plus 20 over x minus 10. And we think to ourselves, ooh, I don't like the fractions. This is a rational equation, and probably the best thing to do to solve this is to multiply everywhere by the common denominator, which in this case would be x times x minus 10. 1 over 1, I don't need to put the 1 there. So if I multiply 1 by that, I get exactly that. X times x minus 10. When I get to the second term, if I am multiplying 20 over x by all of this, the x's cancel, 1 on the bottom takes out the 1 on top, and I get 20 times the quantity x minus 10. When I multiply the third term, it's the x minus 10s that cancel, and I get just 20 times x out there. Let's do the distribution and see what we come up with. X times x, x squared, minus 10x equals 20x minus 200 plus 20x. Okay, I can live with that. It's going to be a quadratic. There's no way to get rid of the x squareds without solving the quadratic formula. So let's move everything over to this side and see how that shakes out. X squared. I had minus 10x's over here. On the other side, I had 20x plus 20x, so 40x that has to be subtracted. Negative 10x minus 40x, that's minus 50x's. The constant was negative here, so plus 200 equals 0. And we can use our quadratic formula to solve that, although it could be factorable, but I'm going to just quadratic formula. X will equal the opposite of b, so 50, over twice a, 2 times 1 is 2, plus or minus, well, the middle term, or the b term squared, 50 times 50 is 2500, minus 4 times 1 times 200. All of that is also over the 2a, or 2. So 50 over 2, 25, plus or minus 2500 minus 800, that's going to be 2500 minus 800, 1700. Alright, that's something that we can work with. Let's use our calculator and find out how that simplifies. Let me get it back so I can see it here. Alright, so I want to get to a new page, and it's going to be a calculator page. And I love my TI calculator for this reason. I can type this thing in, 25 plus, and it's the square root of 1700, divided by 2. And I will find that I have to drive at a rate of, I forgot the number, I didn't look, I guess, 45.6 miles per hour. 45.6 miles per hour. We also have to do the subtraction here. Technically, if we're solving the quadratic formula, there should be 2 speeds that we come up with. So I want to go back to my calculator and tell it to do the same thing, only this time subtract. 25 minus root 1700 over 2. That's saying 4 miles per hour. Ladies and gentlemen, I'm pretty sure that that is an extraneous root. That's not going to help us, okay? If we want to get there in no more than an hour, then on our way to work, we need to travel at an average velocity of 45.6 miles per hour. Good problem. Good challenging problem, and good one to think about. We use that rational equation to answer a real problem. So this is the end of our lesson today. I hope that you have a good night and that you will look at the U-Try as quickly as possible.